Everyone. This is going to be a really quick video on hopefully a little bit more about linear regression. And I'm going to use both Excel and SPSS to actually do these analyses. I'm using Excel because it is a little bit easier to deal with if I would actually want to uh, like try to show you everything that I'm doing here. If I do that, awesome. If I don't do that, some of the stuff just goes on in the background. You never have any idea what's actually going on. And some of the stuff might be a little bit more mysterious than it needs to be. But with any type of regression that we're going to be doing, there are some assumptions that we have. And if we end up having a model that violates these assumptions, that just basically means that the model that we made, even though on paper or using any type of metric we want to talk about, it might look really, really, really good. It's actually garbage. And it's also one of the big reasons why a lot of times some of these particular models might not actually be, might look really good, but might not be all that valuable for whatever its intended purpose was. So let's take a look at a couple of those assumptions that we need to be worried about. So if I flip this over, some of the assumptions that we need to be worried about when looking at the data. And when I'm talking about a linear regression, I'm just talking about what's called a simple linear regression. Many of you might actually know it as y equals mx plus b. In statistics, we look at it more as beta 1x plus beta 0. If we think about hypotheses here, our initial hypotheses are always going to be that in this case, beta 1 equals 0 and beta 0 equals 0. Our alternative hypotheses are going to be that beta 1 is not equal to 0 or beta 0 is not equal to 0. So it can be dealing with any of these sorts of things here. Now, the assumptions that we have to deal with are one, something called a residual is normally distributed. There is a lot of issues out there. If you read a lot of different data science textbooks, they will tell you something other than this. If they tell you anything other than the residuals need to be normal, they're wrong. End of story. Doesn't matter who wrote it or how many people believe it. It's wrong. This is straight from statistics. And unfortunately, a lot of times with data science, um, they're trying to take a pair of 15-week long classes and condense it down into a section of a chapter of a book. So there's a lot of stuff that gets left out, a lot of the nuance, a lot of things that make a model actually work right or not. Another thing that we need to worry about here is that the values of x, and when I'm talking here, if we have a whole bunch of what are called ordered pairs, so if I've got one, two, three, four, and so on, and then whatever the y values are, all of these values here are independent of each other. A couple different ways this can be not true. Three, we have to have equal variance in the range of x. In order to do or look at all three of these things, we're actually going to be spending a lot of time looking at these residuals. When we look at those residuals, if we make sure that they're normal or look at these residuals, we can uh, do all the rest of these things here. But a residual We just basically calculate that by looking at whatever y value we had minus y hat. So this is whatever is predicted by the model. This is the actual data point that we had. So what do I mean by that? Let's say we take all our data, we plug everything in, we do everything we need to. Oh, and I should say that the residual, if we're going to be dealing with the statistics, there's going to be this error term at the end. And the error term that we have here is is where basically we learn how to do all of this stuff. So it's all dealing with the residuals. So if we have a model where it says y equals, uh, say 5x plus 3, and we come up here, I'm not putting any numbers in here for what the actual value is. But what we would do is we'd say y hat. So I plug in 5 times 1. It's 5, 5 plus 3. So this is going to be 8. 5 times 2 is 10. 10 plus 3 is 13. 3 plus 5 is 15. 15 plus 3 is 18. And one couple things that we should notice here, and I'm using really silly values here, but what's the difference between 1 and 2 here? We just added 1. 2 to 3, we added 1. 3 to 4, we added 1. When we're doing our predicted values over here, though, what's the difference here? We added 5. What's the difference here? We added 5. And of course, that 5 actually comes from right there. So looking at all this data, let's say here we've got, instead of 8, we've actually got 7.9. Let's say instead of 13, we got 13.2. Instead of 18, let's say we have 17.8 or something like that. Okay. So just on these, if we're looking at the residuals, we can look at these as y minus y hat or y hat minus y. The only difference between these two is if you have it positive on using one of these calculations, it's going to be negative on the other calculation. So not a big deal. But we need to come up here and we need to look at all of these. So I have 7.9 minus 8. So that's going to give me a negative 0.1. For this next one, I have 13.2 minus 13. So that's going to give me a positive 0.2. Here I have 17.8. I predicted that there should be 18 there. So again, this is going to be negative 0.2. And we go down and down and down and down and down with that. So if once we've collected all of these residuals, we can actually look at them, try to make sure that they're normally distributed. With SPSS, we've got a bunch of different ways we can do that. With Excel, we've also got a bunch of different ways. So if we want to test normality, uh, big things that we're going to do here are we could actually try to use a histogram, or we can use a QQ plot, or PP plot if we're using it, talking about SPSS. We can also do distribution finder, stuff like that if we have SPSS. So a lot of things going on there. So to test for independence, this can be a little bit trickier because we can have different ways things are not independent. A lot of times with a lot of the data that I've actually looked at, if I take my data and I say, okay, there's a zero, -1, -2, 1, and 2, and I plot the residuals, if I end up having something like that where it just fluctuates back and forth, that's telling me that if I'm looking for if it's independent or not, I'm not seeing anything going on here, so I think these look fairly good. I can also use the same plot to tell if there's an equal variance. If I had a data set where it goes like that, you can see that there's this kind of like an arch that's going on here. The data looks like it has a pattern, so definitely not independent here. But if you look at the variance, so from here to here versus here to here, so if we create some error bars and then over here do the same thing, you'll notice that the variance is about the same. Another thing that can actually happen and is fairly popular is we might have out at one end, the variance is just really, really small. So if I create an error bar there, but as we go on, it fans out like that. So now out here, my error bar is a lot larger. With data like this, we'd say this does not have equal variance. Sorry. And we'd have to remediate. Here, this is basically a classic sign telling you to add an x squared term to your model. That's actually going to make a lot of these arches that we see here actually go away. Uh, when it comes to tests for independence as well, that can get to be quite a bit more difficult. Oops. So if, for example, I'm trying to create a model, so it doesn't even have to be like say traditional linear regression model, but just a traditional model. And let's say I want to try to figure out what is, say, the temperature going to be in a given day. If I know that, say, at 5 a.m. it was 50 degrees, at 5:30 a.m., what temperature do you think it's going to be? Probably about 50 degrees, plus or minus maybe 1 or 2 degrees from there. Of and I can create how do I know that at 5:30 the temperature is going to be about 50 degrees, probably plus or minus 1 or 2 degrees, unless there's going to be like a huge cold front or huge warm front that comes through. Basically going to be whatever you looked at before. If we're talking about temperatures in a day, starts out cold at 5, and then as time goes on, temperature goes up, hits a peak, and then temperature drops back down. That's how things work. Because I'm using, say, the temperature at 5 a.m. to predict what it's going to be at 5:30 or 6 a.m., that means that the temperature that I have in a given day isn't necessarily going to be independent of each other. Um, you, if you get into something called forecasting, this can actually be a fairly large issue because if you're looking at what is the stock price going to be for the stock tomorrow, it's going to be based on what is the stock price today, plus or minus a little bit. And then there's the potential for something that would be called a shock to the system, which could be, uh, say, for example, if we're talking about Ford Motor Company stock or Stellantis stock. Uh, the stock may perform in a certain way over a certain period of time, and then You'll have like whoever the CEO of the company is come out and talk with the shareholders about what the stock is doing. So at that point, that could be the change. And if the report is really good, stock price is probably going to shoot up quite a bit. If the stock price isn't very, or the news isn't very good, it's probably going to go down. So in a case like that, even because we're still starting off with, say, what is the stock price today, and using that as one of our variables, that means that those are not independent of each other. A lot of other things that can come up, but those are the two big ones we need to worry about here. So one of the things I want to do is actually try to get or show you how to do some of this stuff and what it looks like if we're using, uh, say, Microsoft Excel. And I'm just using Microsoft Excel for no reason other than it's a lot easier for me to use and show you what I'm actually talking about here. So what I've done is I've come up here and I've created this model. So I'm saying the model is equal to 5 times x. So this is our x column plus 3, and then plus this norm inverse. So this is an inverse normal value. Rand here gives us a random variable. Standard deviation here is 0, or sorry, the mean is 0. And the standard deviation is whatever I have here. And because I put the dollar signs in front of the E and in front of the 1, it's always going to lock it into here. Now, one of the weird things is that's going to go on here is as I try to make any change to the Excel sheet, or if I try to do any calculation, you notice that the values in Rand change quite a bit. So if I come up here, delete all that. So if I'm going to be doing this, I actually need to take my data here, I'm going to copy it. I'm going to paste it here, but I'm going to paste only the values, not the actual function. So here you can still see the function that I put in. Over here, you can see that it's actually just a numeric value. And just to make things a little bit easier, I'm going to come out here, format the values, and look at the numbers. I only need 2 decimal places, so that's good enough for me. Now, if I'm going in and I'm going to use this data, I can come up here and say data analysis, regression, my Y values are going to be all of these. So I've got 100 of these numbers here. My X values are going to be this X column here. And I'm going to look at residual plots, normal probability plots, and everything that I can get. I also have to click on this labels thing here, and I'm going to click on OK. And what you see when we look over here, in this particular case, we know with certainty that I said the model we're going to be using is 5 times x plus 3. And here we're actually seeing that x is about 5. The intercept here is about 3. If we look at the confidence interval here, is 3 contained within that confidence interval? Yeah. Is 5 contained within that confidence interval? Again, yes, it is. And when we look at all of this, one of the interesting things to look at as well is I said that the standard deviation for that normal distribution is going to be about 3. And here we see that the standard error is 2.88. So that's about 3. The R squared value here is fairly large. That's kind of what we would expect. Looking at some of these normal probability plots. Um, so again, we expect there to be like a straight line underneath here. We expect all the dots to be close to that straight line. That's what we're getting here. So cool. the residual plot here. So again, this is the thing where I was saying, if we look at it, we expect the bumps to be pretty much all over the place. We don't necessarily see a pattern. And hopefully we look at the variance on one side and the variance on the other. They'll be about the same. And that is essentially what I'm seeing here. So again, cool. We can look down here and we can see what are the predicted values for Y, what are the residuals, and what are the standardized residuals. And these standard residuals are just the residuals put into turned into a z-score. So nothing too important going on there. Now, a couple things or that we can do with all of this as well. Since we've got our residuals here, I'm going to highlight all of these. And I can also come in here and insert a histogram. And when you look at the data here, does it look like it's a bell-shaped low at one end, high in the middle, then gets low at the other end? Yeah, it does. So this is kind of telling me that the values we were looking at, they actually kind of do make sense. So this is telling me that the residuals are normally distributed. So when I said number one is the residuals are normally distributed, this is what I'm talking about. Something that I've seen and a huge mistake that I know some people make with these is if we go back to the original data here, if I look at these X's here, there are actually some people that will say the input variable or the independent variable here needs to be normally distributed. No, it doesn't. Not even close. And this is actually the data that I'm using here. Does that look like it's normally distributed? Nope. And you know what? I don't care because you don't need to care. If someone says anything different, they are wrong. And that's just like end of story stuff. And I know I'm hitting that pretty hard, but it is an issue that I've actually seen many, many, many times. Now, let's say we're dealing with the same number or the same type of model, but instead of a standard deviation of 3, let's make the standard deviation equal to 15. So we've made the new data. I'm going to copy this, do the same thing that I did before, paste only the values. Now I can go back, assuming that I can get everything on the screen for me to read. Go back to data. I'm going to do another analysis. Everything's already set up the way that I want it to. And here we go with that. The normal probability plot. Again, does this look like a straight line? And does it look like a straight line go? Are all the data points are near a straight line? Yeah. So again, that looks pretty good to me. Don't need that. Looking at the residual plot here. Again, does it look like the variance over here is about the same as the variance over here? Yeah, pretty much. I know if you're to like pull out like some sort of a measuring device and you look at like right in this area here, you're going to say, well, here's a 0, here's a 10. So that's a variance of 10. Then you look out here and you've got negative 30. And you look out here and you see that it's a positive, what, 40. You say, well, this is a distance of 10. This is a distance of 70. Clearly, that's different. And I understand. But we're not looking at, say, any particular given points. We're looking to see, do we have like a fanning or all sorts of other stuff going on? And if you move these over a little bit, they just get mixed in there. So I'm not seeing anything in here. I'm pretty happy about that, which is cool. Again, looking at the standard error, I've said that standard deviation should be 15. The standard error here ends up being this 15.75 or 15.76. So again, it's about 15, not exactly. Even though this is the exact same model, if we look at what's going on over here, I'll try to zoom in on this. We still know that this model is 5x plus 3, but this time it's telling me it thinks these coefficient here is 5. We have a statistically significant value here. And then looking at these two values, is 5 between those two numbers? Yes, it is. So the model is correctly predicting what that coefficient for x should be. Up here, though, we look over here, all of a sudden, because there is so much variability, we can't really tell if there's a significant difference between 3, which is what is in the model, versus 0. The model is predicting that instead of being 3, it's actually 1.05. If we look over here at the confidence interval, is 3 within those two numbers? Yeah. But because there's so much more variability in here, we actually just lost the ability to see if the intercept is actually statistically significant. We know it's part of the model, but because there's so much noise in the data, we just can't tell. So that's something that we need to be worried about, or sometimes need to look at. Again, dealing with the residuals. So if I click on all of these, I can do insert histogram. So do these data look like they're normally distributed? Maybe, maybe not. But one of the weird things is sometimes you can't really tell based on this. So if I click on these, bin width, let's say I make that 8 instead of 12. Does that look a little bit better? Starts low, gets high, then gets down low again. So with some of these, you just have to look at them and try and figure out, does it look good enough to you or not? I already know that the answer is these are normally distributed, even though looking at it like this, it doesn't look like it's normally distributed. Unfortunately, that's how some of these models actually work. Even if you have 100 data points, sometimes you don't have enough data to make a really good sound judgment call on some of these things. Now, look at this one more time here. But this time, I'm going to make it so that we have that fanning shape. So if I look at, so I'm actually going to take some of these and plot them over here, just so I can go back and we can actually put these into SPSS and take a look at them later. Now I'm going to change the model a little bit. So I'm going to say that the error here, so this whole inverse normal thing, instead of being normally distributed, I'm going to say it's equal to 0.2 times whatever the x value is, and then from there say times the normal inverse and all that. And what's going to happen there is when we flip all that stuff over, now that I can take this, I'm going to copy, paste it over here. So now if I go back and I do the same analysis again, it's data analysis, regression, everything's already set up. Apologize for this. Trying to do this on my laptop screen and some of it's not working out quite right. So looking at the data that I have here, does this look like it's a straight line and all the dots are on that straight line? No, no, it does not. if I look at the data here and look at this plot here, do you notice that the orange line still makes a straight line, but looking at uh, the blue dots here, these are the actual. So this would be the orange things here are Y predicted, the blue things are uh, Y actual. So if we're looking at the residuals, we see that there are going to be some issues here. So we see that there was some really weird stuff going on here. That doesn't look quite right. If I look at the X residual plot here, notice how out here uh, these are really close together than out here. So we have oops, sorry, definitely got some of that like fanning pattern that's going on. This again is telling us that the model that we just made, even though it might look really, really good, it's violating a lot of the assumptions. And when we do these with multiple linear regressions, we need to be looking at the exact same things here. So I'm going to delete that. Looking at what we have here, again, we know that the model itself is y equals 5x plus 3. But look at what's going on here. It's now telling me that the coefficient for x is 21. 5. But I really can't tell that. Does the confidence interval here even contain 5? No, not at all. We can see that the standard error here is really, really huge. So this is another thing here where R squared is fairly low. And because of all the odd variance, we really can't see that. If we go back to what we had before, so R squared, even though we had huge amount of variability, R squared was actually still pretty high. When we had smaller amount of variability, R squared was still really, really, really high. But out here, now that our standard error is really large, this R squared is going to be fairly low. Still going to create a statistically significant model here. It's just the coefficients here are totally wrong. So again, part of what's going on here is I made it so that you're multiplying whatever this sort of random value is by 20% of whatever this is. If I make this say 0.02, and then drag that down. Now it's going to be doing pretty much the same thing. So I can copy, paste just the values over here, data, data analysis, blah, blah, blah. Yeah, that's everything we want. And now that the variability is a little bit smaller, instead of 20%, it's only 2%. This is actually starting to look like it's hiding some issues that we have. And again, that is something that can and will happen with real data. If I didn't know any better, I'm looking at that. Do I think that looks like it's normally distributed? Yeah. So that would even be fooling me. Looking at our plots here, this is giving me a little bit of a cause for concern. Because down here you can see that basically all these orange things are covering up the like the teal things. And then as we go up further, you can see that a lot more of the teal is peeking out. So that's giving me this concern that there might be some fanning going on here. And then again, looking at the residual plot, it's fairly clear to me that there is that fanning. And when we go and we look at our R squared value, that actually looks really, really good. The model that we have here, we know that the coefficient is 5. This is telling us that it's 5. The confidence interval here contains 5. So that's at least working. The p-value here, again, because of the amount of variability within the data, we're probably not going to see what the intercept really is. What is 3 within that confidence interval? Yeah. Uh, because it's going from a negative value to positive, we've decided that it's not statistically significant. So based on the data that I have here, I would actually call this model y equals 5.02 times x, and then be done with it, even though it should be 5 times x plus 3. We can't tell that that's actually statistically significant. So I'm going to copy this over here. So now let's try to do these in SPSS and see what sorts of things actually go on there, just so that we have some idea about what's going on. So I'm going to have to stop this share real quick. Get rid of a couple things that are up on my screen. Nothing that's actually embarrassing, just uh, some stupid stuff dealing with Zoom. And I'm actually going to share my entire screen with you so you can live through all the blood-curdling, annoying things, same as me. And even on my computer, SPSS can take a bit of time to try to load up, but it's getting there. All right. So I don't want any of that. What I do want are these two data points, or these two sets of data. So a couple things we can do here. I could either save this file and then try to import it into SPSS, and SPSS is not going to like that at all. Or I copy and paste, but paste with variable names. And there we go. Now, if I want to do a simple linear regression with this, what I need to do is I need to come up to Analyze, and then drag down here to Regression, and then slide over here to Linear, click on Linear. Y is what we would call my dependent variable or my output variable. My independent variable, even though it may or may not be independent, will go in here. For multiple linear regression, we need to worry about these things for right now. I'm just keeping it as enter. Now, if I come up here to statistics, something that I might want to look at, confidence interval. Need to want to look at Durbin-Watson for residuals and collinearity diagnostics, or simple linear regression. That's not a thing for multiple linear regression like we'll go through next time. That is a huge thing that you definitely need to be concerned about and dealing with. I'm going to click on here and say continue. Plots, histogram, normal probability plot. I'm even going to say produce all partial plots, and then hope that the software actually does it. I can save a whole bunch of stuff in here if I want to. Not too worried about that. We can do prediction intervals and so on. That could actually be fairly useful depending on what it is we're trying to do here. Some of the other options here, don't have to worry about any of that. Style and Bootstrap, I'm not going to worry about that. So I'm just going to go ahead and click on OK. And we have here an estimate for the standard error. We have our NOVA table telling us essentially the how much of the variability and everything is accounted for. And when we look down here, we notice that the says unstandardized coefficient, so the value that we believe should be comes out to be 5.015. We know that should be 5.0. The large t value here tells us that it's statistically significant. The confidence interval that we have here tells us that the coefficient could be anywhere between what 4.98 and 5.05. We know it should be 5. This is again, that's cool. VIF here is equal to 1. For right now, that doesn't mean anything. Later on, we do need to be worried about it. Some other stuff that comes up that we may or may not actually care about. And then here, for whatever reason, we're looking at a histogram of Y. I don't know why either. We don't expect this to be normally distributed. That's just given. Well, here it says a regression of standardized residuals. Does that look normally distributed? Maybe, maybe not. Using the PP plot here, you can see the straight line. Do most of these dots seem to be close to that straight line? Yeah. All right, cool. Now, if we're going to look at the other data set, the one where we know that there's going to be some fanning, can actually highlight all of that, copy that, paste it over here, and oops, try that again. You don't want to start doing two things too quickly and screw them up. So copy, come over here, paste with variable names. So there we go. So now if I go back to analyze, so again, analyze, regression, linear, everything is ready to go. I'm going to click on OK. And looking at this data, uh, so this is actually giving us uh, an idea that the coefficient for x should be 5, which is what we know it should be. We see that there's a very large standard error here, but even so, r and r squared are still fairly large. We come down here, look at the data again. Does that look like it's normally distributed? Maybe, maybe not. Does this look like all the data points are up against the line? Absolutely not. This is one of the signs that something is not working right. Nice thing about, I'll try to do this slowly. Nice thing about SPSS, we can go to Analyze, go down to Regression. And if you have a regression diagnostic test like I do here, you could click on that. You could come up here and do the residual heteroscedasticity test, which is trying to figure out, does the variance seem to be the same? So Y is going to be dependent. X is going to be the independent. That should be about it. And then I can click on OK. It's going to do a thing. And non-constant variance test score, large chi-squared value here. This is telling me that there is a significant issue with the variance not being equivalent or equal all the way through. Just to see what that would look like if we did it with the old data. I probably should have did that first, but oops. So if I'm going to go back to the old data, copy, and then paste it in here. And again, go to Analyze Regression, Regression Heteroscedasticity test. Yeah, that's a mouthful for anyone. Again, everything's set up. Going to click on OK. And this time it's coming up with a very small chi-squared value, which is telling us that the significance is going to be a value here. The p-value is going to be very high. So this is telling us we don't seem to have an issue. Now, if you have some of these other things on here, I've actually never really played around with them. So like it says here, regression diagnostic test. Who knows? Let's see what happens. So dependent variable is going to be y. X is going to be the independent variable. No idea what this is down here. Diagnostic tests. Uh, oh, these are the tests that we should probably be worried about the most. But I'm not doing any of these, so let's see what happens. Click on OK. And is that really all that it just did? Oh, okay. So here's everything. So what it's doing is it's using a bunch of stuff that comes from a different software program. And what we want to be worried about are like the studentized Bush-Pagan tests here. Again, telling us uh, essentially we have equal variance. So here's another one. P-value is really large. That's telling us again that we basically have equal variance with this data. So if you can use that to do something, awesome. If not, don't worry about it. Usually looking at histograms and looking at the QQ plots is more than enough. With that, I'm going to say everything that we talked about today or in this video is really useful and also going to be used when we do the multiple linear regression. That's a little bit different type of a thing, but uses the same ideas as we're dealing with here. So with